Okay. So in this problem, we need to find the influence line for the moment at C. There's C. Just to help you visualize it, so we're going to have to come here and probably cut this structure. And you need to decide whether you want to work the left side or the right side. Either one would work. But it looks like the left side to me looks like it's going to be less trouble. Do you guys agree with that? Okay, so that means that what we really want is our reaction at A. We would have a reaction at B also. And of course, we're going to have our unit load up here operating at any distance x it chooses. So before we get started, in order to be able to find the moment at C, and since we've selected the left-hand side, we're going to need our AY reaction. So we've done this a few times now. How do I find AY as a function of this position of the moving load? We're going to sum moments at B. So again, I'll use right-hand rule for my sign convention. So we'll sum moments at B and make sure we're in equilibrium. So what's going to be the moment created by this unit load about B in this drawing? In this position, it's going to be positive. And what's the distance going to be?
10 minus x.
Yeah, if I were to draw a little line right here, this distance would be 10 minus x. So the moment arm will be 10 minus x. And then, of course, we have the reaction at A, and that's going to create negative moment. The force would be AY. And, of course, the distance between B and A is given here as what? 10 feet. So we can find the reaction at A. Divide everything by 10. It looks like it's going to be 1 divided by x over 10. This is kind of interesting, too. You'll notice that x goes from 0 to 15. What happens when x is equal to 15?
You get a negative.
You get a negative. And does that make sense if my unit load is all the way out here, pushing down? Then A has got to also be down to keep this end from what? Wanting to rotate up, right? So that makes sense. It calculates it. I like that. Pretty cool. All right. So now I'll draw my free body diagram. I'll look at the first 5 feet because we've decided to work to the left side. I have my reaction at A, which we've just solved for, 1 minus x over 10. I am now looking for the moment at C. So there's my positive moment at C. And I'm going to assume first that my unit load 1 at some distance x is in that range. So what's that range that's acceptable here? That's going to be when x is between 0 and 5. So how do I find the moment at C? We've done this a few times. We're going to sum moments at the cut that we just made. Make sure it's in equilibrium. And what do we have? We've got our moment. With my sign convention, that's positive. How about this unit load 1? What kind of moment does it create about C? Positive or negative? Positive. There's the force. What's the distance from the cut to here for a given x? 5 minus x. Then what else do I have? This guy, and that's creating what kind of moment about the cut? Negative. So the force is going to be 1 minus x over 10, and the distance is going to be 5. So let's solve for the moment. What do we get? Oh, I did that wrong. I wrote 5x instead of... This is 5 minus x. Right? That's a typo or a do you call a typo when you do it with your hand? An error. All right, so if you look at this, I've got 5, and then I've got negative x. Over here, I've got a negative 5, right? So that cancels. So I'm left with negative x plus 5x over 10, which is a half. So I've got negative, is that right? Negative? Yeah. Let me think for a second. Yeah. So it looks like negative x over 2. Did I do that right?
Wait, why wouldn't it be x? So wouldn't all the signs change when you move the moment?
Oh, yeah, it's going to be positive.
But wouldn't that make it just regular x if it was all positive?
No, because this one is negative x, and then this next makes it positive x. So we got a negative x and a positive x over 2. So that gives me a negative x over 2. You put it the other side, you get positive x over 2. I think. Is that right?
Wouldn't you have 2 positive x's, though?
No, this one's negative, and then this one's positive. See, negative, negative? That one's positive. Okay? That tricky algebra, I think that was 9th grade. Everybody successfully complete the 9th grade? I know I struggled. It was tough. My problem with the 9th grade was getting home without getting beat up. That was my biggest problem.
Oh.
Yeah, I had lots of trouble.
That's
I had lots of trouble.
Did you like influence like your son leader, or was it like you just got?
That's a different story for another time. I'd rather not commit that story to the internet. But if you're interested, I could always tell you about it.
Kind of admitted it.
All right, so let's do the next one. This is me ignoring that and moving on.
You can't ignore your problems forever.
All right, so my reaction is still 1 minus x over 10. I still have my internal moment at C. The thing is still 5 feet, except now my unit load has moved. Now it's somewhere between 5 and 15. It's over here. So, as I mentioned before, Elvis has left the building. Elvis has walked away from your beams or your free body diagram. So now I just have to do this. So let's do that. So just like before, I'm going to sum moments at the cut, put it equal to 0. My internal moment is positive. My reaction moment, or the moment created by this reaction, is negative. And it has a force of 1 minus x over 10 times 5 feet. So when you solve for the moment at C, you get 5 minus x over 2. And now you just plot that. So let's see what our moment looks like. So my ordinate will be the moment at C. And I've got, there's 5, 10, 15. So from 0 to 5, this is my equation. So I plug in x equals 0, I get 0. I plug x into 5, I get 5 over 2. And that's a straight line. So there's my moment influence line segment from 0 to 5. Now from 5 to 15, this is what I put in. So I start with this equation at x equals 5, and I get 5 halves. So it does match. I plug in 10, what do I get? 0. And I plug in 15, what do I get? Negative 5 over 2. So there's my influence line for the moment at C. Now we know moment, in some structures, the difference between positive and negative moment is significant. So where would I go stand to create the biggest positive moment at C? Well, the biggest ordinate value is right at C. So I go stand at 5 feet, and that creates the biggest moment at C. Positive. What about the biggest negative moment? I'd go all the way over here and stand at 15. That should make sense. If you stand over here, you push this down, you'd expect a big negative moment through here. But if you stand right here in the middle, it's like a simple supported beam, you'll see a big positive moment. So this is really helpful if you're designing a bridge out of reinforced concrete, because it tells you what kind of positive bending moment you're going to have to deal with, which is reinforcing steel on the bottom of the beam and the tension side. And this is negative moment is called compression steel, but really it's causing tension in the top of the beam too. So if you get a chance to take reinforced concrete design next fall 2020, you'll have to keep track of those two things. If you take steel design in the spring, usually steel beams, you just take the maximum moment. They're usually symmetric. It doesn't really matter whether they're positive or negative. Any questions about that? All right, we're moving along. This is great.